I'm just recording this. So the goal, as people sometimes wonder, what are the applications of group actions? Of course, you know there are many applications, but here we will give an application which is a little uh, involved. Okay, so the goal here is to show, and I will define what this thing is, but let me just write it like this: is PSL to R, PSL to, I'm sorry, it's not PSL to R, it's PSL to C. PSL to R is also simple, is to show that PSL to C is simple. I will define what PSL to C means. And we will do this using group actions and inversive geometry. Just fancy words. Using using group actions. So what we will do about group actions is that this will be a group. This is some kind of matrix group. It is some kind of matrix group. I will tell you what it is. It's some kind of matrix. It's projective special linear group. And you will make it act on some space. And by acting on some space, you will be able to understand the group, because there will be certain things about the space, So basically, when you act this on the space, then you can ask questions about the group where the language of the question comes from certain things about the space, right? So you can ask more interesting questions about the group, which means you can get answers, and which means you will get some interesting subgroups of this group, right? And using those interesting subgroups, you can show that it has no normal sum. That's kind of, so that's how group actions come. Using group actions. And another feature which is slightly distinct is inversive geometry. This is sort of, maybe I don't know if I can say, in a way, yes, in a way it subsumes the Euclidean geometry. In a way it subsumes Euclidean geometry, but yeah. But we will see. I will follow the book so that if you want, you can later go back and look at it. And I will mention the reference also. Let's see how well I will try to. I will obviously complete it, modulo checking the details. But the reference is this book on groups, simple stuff, very readable book. Groups and geometry. Actually, there was a workshop in St. Xavier's, in fact, from which college Arnav belongs, on this elementary things. So groups and geometry, same book actually is also called Groups and Geometry, and name of the workshop is also Groups and Geometry. Yeah. By Lindon, and only one author. Yeah. So I've read this around 2 months back. So I mean, I obviously let's see how can I do it. By Lindon, LMS, London Mathematical Society. Yeah. And you may be thinking what, but you see, if you study this and you solve all the lemmas and fill all the details, those are your exercises, how you become better in group theory. You don't become better in group theory maybe by reading the same chapter again and again, right? Become better by looking at something. It's not very difficult, but slightly new. Okay. Yeah. And this is, yeah, it would have been good if I had the book. Chapter 8, which is called Inversive Geometry. And then they use inversive geometry to get hyperbolic geometry from here. But we will not discuss hyperbolic geometry. And before this, they have something called affine geometry, which is not very good. Okay, so this is. So let me begin with some definitions, and then we will do this. As you understand, I will also have to look at the things like that. Involution. Right. So the first concept that comes here is inversion in a circle, or yeah, let me maybe make a definition. Let me say inversive line. Okay. So what is inversive line? Inversive line, because if I say inversive line, then I can define two things at once. So inversive line is the collection of lines, or maybe here, obviously the whole game is to change the notion of lines. So I mean, but yeah, simply put, you have Euclidean lines, meaning that the lines you are used to. Union Euclidean circles. Right? And they have actually not defined inversive lines here. Right. So yeah, maybe this is a bit premature. But anyways, an inversive line is just a union of Euclidean lines and Euclidean circles. I just call everything inversive line. But actually, I made a slight mistake. Actually, I should have first defined the inversive plane. Okay? So the goal here is to give you the landscape of the chapter, so that whatever I'm not saying is some simple things which you can fill in. It's like fill in the gaps. That's what I'm not saying. Like I will, something is saying some map is surjective. I'll not prove it. You can just, if it's simple enough, you will have to prove it on your own later. So inversive plane is just the Euclidean plane. So in this case, it's just R union. We'll just take a point at infinity. Okay, because the functions that we will define, the functions that we will consider, which will be bijections, functions that we will consider will be bijections on R2, and you can understand the bijections come from group actions. Okay? And but sometimes the point 0 may go to infinity inversion, and so that's why if you put infinity, then it becomes a proper function. Otherwise, you have to say make some exceptions. So inversive plane is this. Now, don't ask me the don't ask me where the infinity sits exactly. I could get into that, but it is not needed at the moment. Just imagine that there is a point again, and use your sensible model. The main concept here, these two are like, I could have said it in words actually, but the main concept here is inversion in a circle, or yeah, that's why the book is a book, and I'm not that good, because I should have not defined inversive line first. But anyways, inversion in a, now I have to write Euclidean circle. So inversion in a Euclidean circle, this is going to be a function, and no, let me change it. Inversion in an inversive line. So what is this? This is a function. This will be a function. Let me call this line C. Okay, and then this thing is a function which I'm denoting by gamma C. Okay, it will be, and let me also call this E star now. Okay, E is sort of Euclidean, and star is sort of Euclidean plus a twist, plus not sorry, not a twist, sorry, and a point. I didn't. So this the definition of this is a function which is from E star to E star. And now I will not write a formula for the function. I can write, but I will not write a formula. You can write it, but will not write a formula. I'll describe it in geometry. And these functions, we will make a group out of these functions. But first you see, what is this function? So function is very simple. If C is an Euclidean line, okay, then what is gamma c? Just reflection about the line, okay, then it is just a reflection. Let's write it in words. Then gamma c is reflection about the line. Is it language? Is this language correct? Reflection about the line, right? Reflection about the line. I mean, I was slightly wrong. I mean, we no, correct. That's fine. The PSL2C is orientation preserving functions of this subclass of these functions. Not all, not the entire group that we will consider. And this thing you will see in complex analysis as well. It connects with a lot of other things. That there they take PSL2CR and it gets very interesting. Complex analysis connected with modular forms and number theory, and then everything. Basically, yeah, a lot of things. So, anyway, so is this okay, everyone? This function on Euclidean line, just reflection. Yes or no?
But
Yes,
what
sir.
is the inversive plane? I don't get it.
So just think of the inversive plane as R2 and with a point at infinity. Yeah. So it's not, so it's a plane maybe which you cannot imagine. You can imagine R2 and you can just imagine that there is a point very, very far. Okay. Okay.
Oh.
Yeah. I mean, I can say it, but it's not needed. Just imagine that it's a point. Otherwise, I'll say that it's a point and then there is a topology with something not needed. Even in simple terms, it can be said, but leave it. This, like this. And then point is that how do you generalize a reflection about a line to reflection about the sun? Please try to give me some answer to this question. How do you reflect about a circle? Because that is what the definition is going to be. What is, have you ever done something like reflection about a circle? Have you ever thought about it? Anyone? Reflection about a circle you would have done. I remember in JE, the JE books also, they have something, inversion about a circle. Even if you have not seen the Olympiad side, it's not important.
I don't know.
Okay. Vaishnavi, anything here?
No, sir.
Okay. Okay. All right. By the way, yeah, don't call me sir. just yeah. Okay. So then I'll just define. I mean, so if C is a circle, then what is a definition? I mean, it's just going to be something very. There are several ways to. So when you learn more mathematics, you will see that there are several ways to get to the definition. Either use geometric intuition or. But anyways, at this point, it's okay. So fine. So C is a circle, and what will be inversion? So inversion, what will it be? It will be something that takes a point in the plane and returns a point in the plane. Step number one, that is correct. And what should inversion be? It should take something outside the circle to something inside the circle and inside to outside. No doubt about that. Kind of, that's what reflection is also doing. Because, I mean, look, a line is like a circle with infinite radius, right? And you see what is happening. So it's that point at infinity. That's what the line is. And now you can understand like what is happening, right? I mean, that point at infinity is not really moving when you reflect. Right? I suppose that's it stays there, right? Yeah. Now why? Because actually that's on this line. That's on the circle. So that line if you view a line as a circle, then that point at infinity is on the line. And when you're reflecting about that line, the line is fixed, the line doesn't move, right? And so that point at infinity also doesn't move, right? And so basically here also we want that the circle should not move. I mean, not just that, the points on the circle, none of them should move. They shouldn't even go to any other point on the circle. Point-wise fixed. But anyways, all this talk, I can just give the definition. So the definition just says that you take a, there are many interesting ways to define this, and Olympiad mathematics is filled with applications of these things, but just take the point P, where do I send it? I have to send it to somewhere inside the circle. So what's a good way to do it? Now, forget about what the definition should be. Think about what is something good that you can do at this point. That's what mathematics, right? I mean, think about what good you can do to, how can you naturally take this P inside the circle so that that point comes outside to this point. What's a good way to do that? Right? So you can do it if you're an algebra person, you can do it in some way. If you're an analysis person, you can do it other way. But basically, it will be equivalent to this, that you have this Q, and then you send it to the Q with the condition that this distance times this distance should be R square, where R is the radius. So with this condition, you send the point P to Q. Okay, this condition and the condition that it's on the line OP. Then it's clear, right? Function is clear. Yeah. All right. Okay. So that's what it is. This is called inversion in a circle. You can read, there is a lot of material on this. You can read and study and get intuition. And it's like what do you say? It's a rare source of it. It's I mean, nothing is rare, everything is there. But still it's sort of one of the unique sources of intuition that inversion can give you in mathematics. Because it's different from other things, some sense. You can show that there are many equivalent ways, but I'm not going to do all that, but I'll just mention it. That even if you do something like draw, like I said, if a geometry person, then geometry person, if you ask, as I said, if you ask what good can I do from this point P to get land inside Q, I'll draw a tangent and draw perpendicular. That's a good thing. It will surely get me inside. It's a nice systematic way to get in. And that also, no doubt, takes you to the same place. You can prove all that. That can be power of point, play around with it, prove it. High school mathematics. So these definitions are same. All right. So maybe I will keep this picture here and I will continue. Yeah, we should go slightly faster. So I have defined gamma C. Now you check. Gamma C is always a function from E star to E star. And so you just think of it as a reflection about a circle, right? The farther a point is, the closer it comes to zero. The zero goes to infinity. You can check that, right? You can check that, right? So if you have OQ times OP is equal to R square, that's what it is, right? But if P is equal to O, then this is zero, correct? And so Q should be infinity. Otherwise, right? It's not a linear thing. It's not a linear thing. Circle is sort of a convex, reflex. But what you should check is gamma square, which is gamma, and these are the important things to check. Okay? This thing is equal to identity. Very important. It's probably the most important. Okay, you will check it. It's trivial, but you should check. As you know, reflection also has, this one here means identity, right? I mean, it should not be like this. I mean, I should write maybe ID. Otherwise, it becomes like a characteristic function. Right? Return 1 on the set and 0 outside this. It's not like that. It's ID of each star. Okay. These things you can check. And now comes the interesting things. You have defined a function, or you have defined many functions. Right? For every C, we have defined a function. For every circle, we have defined a function. For every line, we have defined a function. Now, whenever you define a function from a set to a set, you must ask maybe that what happens, what does it do to interesting subsets? You guys get my point? Yeah? Correct? You must ask what does it do to interesting subsets? Or what is the inverse image of interesting subsets? These are the two things. And you will see that all the definitions in mathematics, which are related to functions, are defined in this way. Like continuous functions. What are continuous functions? So that the inverse image of certain interesting subsets is interesting. And what is interesting there? It's open. Because in topology and geometry, in that sense of geometry, one can distinguish, but metric sense, that is an important set, right? Measurable, if you know. And this linear algebra, what does it do? It takes lines to lines. I mean, if a function takes lines to lines, and just some other conditions, you can prove that it's linear. It's difficult, slightly difficult to prove, but it's true. Usually people don't define like that, but it's correct, right? If you think about it. If you try to prove it, you will see. It's also proved in this. It actually becomes continuous of its own. So here we will ask, what does it do to interesting sets? And so the question would be, what does it do to lines and circles? Okay. And now is the thing. Okay. So I'll just write a few things, and this will suggest to you that what I'll write next is true, but I'll not prove any of them. These are all, you can read it in the book, or you can try to prove it, or just work it out. So this, and then if you can ask me, okay, gamma C, if you take C, then what is it? Please tell me. If you restrict this to C, then what is it? What happens to points on the circle? They don't move. Do you people see this? Yeah. If you take a point, so reflection may for line, it is absolutely clear. But here, use this definition. So P goes to Q with this property. So if P is on the circle, then the output is the same point on the circle, right? No? Yeah, you've seen the definition for the first time, I think that's.
मैप भी समझ नहीं आ रहा.
Sorry?
मुझे मैप समझ नहीं आ रहा.
Okay, right. So Vaishnavi, can you explain if you have what is this map doing?
Okay. It's a circle only. But it's fixed.
It is fixed, right? The circle, every point is fixed, right? But
Yes.
in general, Arnab, see, what I am just, Vaishnavi, can you explain the function in general? If I take a general point P, then what does gamma C do to that point?
Okay. Like it makes that point to bring inside that circle.
Okay. Right. And where does it take it?
Like somewhere.
Okay. Let's say it takes it to Q. Yeah. Take your time, think, and you can tell me. That's okay. Means that, yeah. Tell me. What is that Q? That is the what that's for the question. Yeah. So think. This definition is already written here, so you can use this. Arnav, you tell me, or any one of you tell me.
R क्या है यहाँ पे? What is R?
R is the radius of the circle, right? Small r is the radius of the circle.
If the point P is far away from the circle plane, then
Right.
how can the OP and OQ multiplying and giving the radius? How?
Why not? Then OQ has to be very small. No?
But they're not on the circle, right? They're
Yeah, but if it's very far, if P is very far, then Q has to be very small. That is the condition that is forced, right? So P goes to Q such that this condition is satisfied. You can't do that. If it's N, then you take 1 by N, then the product becomes 1. If this distance is N, then you take this distance to be R square by N. You can always do it.
Yeah.
Right? So is it definition is clear? Okay. So now the one, so just define it. I mean, just think about what the definition is, and then you ask me on the other side if it's a problem. I will give you a small PDF where we discuss this in very elementary properties, but we'll meet after 10 minutes. Okay, and then